Thus far in the course, we've looked at different classifiers. So we started off looking at how genetic programming can be used. Genetic programming can actually produce a classifier. The last section we looked at neural networks, and we looked at different types of classifiers and neural networks. We looked at single layer classifiers that perform binary classification, and we also looked at multi-class classifiers where you'd need more than one hidden layer in your neural network. So what we're going to look at in this lecture is decision trees. Decision trees is basically one of the classic methods used for classification. It's a supervised learning method. So like I mentioned, it performs supervised learning. As with the other classifiers, because the learning is supervised, you usually have a data set. That data set contains instances, and each instance is usually made up of a set of attributes for that entity and the corresponding label or target value indicating which class that's in. You could also have a third set, a validation set, and the validation set can be used to actually tune the parameters for your classifier. So usually when you get a data set that's made up all of these different instances, you divide into training and testing. Training is used to create the classifier, your training set, and your testing set is then used to see how well that classifier generalizes. How well can it actually predict the class of unseen data. The one good thing about decision trees and an advantage that it has over neural networks is that it's interpretable. So if you look at the tree, provided it's not too big, you can actually read exactly what's happening in terms of which attributes are important, which attributes didn't count and were not included, based on a particular scenario of attributes from the root to the leaf node. You can work out what attribute values would actually contribute to something being in a class or not being in the class. So generally these classifiers are interpretable. The problem though is that the size of your tree could be very big, and in that case it's not easy to read manually. And that brings us to the whole idea of tree size. One of the disadvantages of decision trees is the tree size can get very, very big. And for that reason, a limit is set on the tree size. Another thing that researchers have done is they prune the tree after an induction algorithm is applied to the tree, or they reduce the number of iterations with the aim of getting smaller trees. So how are decision trees created? There are algorithms that exist that are used to create decision trees. There are a number of different algorithms. We call these induction algorithms. The most popular algorithm is something called ID3. There's variations of ID3 as well. There's more recent versions of it like C45. So if you're dealing with the package Becker, which has a number of machine learning tools built into it, you'll see there's different types of classifiers, and ID3 has different versions and they have different names like C45. So before we look at ID3 and we look at how we can use it to create a decision tree, just a quick reminder of what a decision tree looks like. We looked at decision trees during the lecture on machine learning when we did an overview of the different machine learning techniques. So essentially what happens, remember in your data set you have instances, and those instances are made up of attributes and then the corresponding class for a combination of attributes. Now the attributes that you have in your training set, those attributes form the nodes, your internal nodes in your decision tree. So if you look at the example that's on the screen, the main aim behind this decision tree is to categorize a fruit as being a papaya or not being a papaya. And you can see there's two main attributes in yellow, color and softness, for the data set, and these seem to be the two attributes or features that contribute to the decision. There may have been other attributes, but during the whole process of induction where the decision tree was produced, only these two attributes actually resulted in the tree or were contained in the tree, which means they contribute to making the decision. So if you look at the color, if it's not pale green or pale yellow, then it's definitely not a papaya and it won't be tasty. So the whole idea, is not to work out whether it's a papaya, but to work out whether the papaya is tasty or not. So we know it's a papaya, but we're trying to work out whether it's ripe enough to eat and would it be tasty. So if you look at the color, if it's pale green or pale yellow, then it will be tasty, but if it's any other color, it's not going to be tasty. And then after you look at the color, if it's either pale green or it's pale yellow, that's not the deciding factor. You then have to look at the softness, and the way the softness is determined is by palm pressure. So slight palm pressure, you don't want to press the papaya too much because it's a very soft fruit. So if the palm pressure, the papaya gives to slight palm pressure, then it would be tasty. Otherwise, it's still too hard, it's not ripe yet, so it won't be tasty. So this is a very, very simple example of a decision tree. We're going to use this as a case study throughout the lecture, and you'll see it's also a case study in the notes. And basically, it's going to be used to show you how you work out different measures that ID3 need, like entropy and gain, and also how you can actually create a decision tree from this data set. So in the notes, you'll see there are examples of how you can actually work out entropy and apply the ID3 algorithm for the first part of the decision tree. Creating the rest of the decision tree is going to be left as a tutorial for you to work through, and that'll be next week's tutorial, which will be on decision trees and K-means algorithm. So if you look at this data set, the class that you're basically trying to categorize things into is whether to play netball or not to play netball. So it's a no or a yes, which is equivalent to a 0 and a 1. You can see there are 4 attributes, and the attributes are outlook, temperature, humidity, and wind. So the outlook can be sunny, it can be overcast, or there can be rain. The temperature also has 3 values. It can be hot, mild, or cool. Humidity, there's 2 values it can take. You can either have a high humidity or you can have a normal humidity. And with the wind, you either have a strong wind or a weak wind. The numbers that are listed under day is just the data collected over 14 days. And what this is used to predict is whether a team should go ahead and play netball or not play netball. So you'll see the values of no or yes indicate for that combination of attribute values, should netball be played or not. When we apply induction algorithms to produce the decision tree, the induction algorithms determine the dominance of certain attributes, or well, of all the attributes, and depending on the dominance, the attribute will be placed in a particular position as a node in the decision tree. So one of the measures that are used to actually work out dominance is something called gain, and gain uses entropy. So if we look at working out a gain, the gain will be used initially, all the attributes of gain will be calculated, and the attribute with the highest gain value will then form the root of the tree. And similarly, as you move lower down the tree and you decide to add on other internal nodes, gain will be used again to determine which attribute value to add on as the next node. So firstly, we're going to look at how to work out entropy, because this is used in the equation to work out the gain. So your trophy is represented as E of D. Our D there represents the decision to be made. So for example, whether you're going to decide to play netball or not, that would be the decision. Alternatively, if you want to look at whether a flower is a rose or not, that would be the decision. So different classification problems will have different decisions. Basically what happens is the entropy is calculated by taking the negation of the probability of a particular class being in the instance set or the set of instances, and the log to base 2 of that of the same probability. So if you look at the data set we've just looked at in the previous slide, there are 14 instances, and some of those instances belong to the class yes and some to the class no. So that would actually be used to calculate that pi of I value. So it belongs to the class or it doesn't, and we're basically adding up the number that belongs to the class and dividing by the total number of instances. So if you had to define a P of I, it's the number of instances of that class I that basically occur in the data set, and we're dividing that by the total number of instances. So if we look at the example of the data set we've just looked at now for whether to play a netball or not, the first 2 probabilities there are for the first class, which is yes. So 9 instances of 14 instances had a label or target value of yes, and 5 instances had a label or target value of no. So the first product there is to represent the class yes, and the second product is to represent the class no. And the overall entropy for that example is 0.94. So the gain is actually used to decide which which attribute will go where in your decision tree. It's also called information gain. So if you read the literature and you come across information gain, it's the same as gain. So usually what you're doing is you're working out the gain for a particular decision. So for example, whether to play netball or not. And the gain also takes into consideration a set of attributes. So in the example we've just looked at, the attributes were things like outlook, temperature, humidity, and wind. Sorry, excuse me. And so that's your attribute set A. So in calculating the gain, you can see we also need to calculate the entropy, which we've just looked at. So we look at the overall entropy, which is E of D, but we also look at the sum of the probability of a particular attribute for a particular value occurring in the set of in the data set, and then we look at the entropy for that particular attribute with a particular value. So to give you an example, if you looked at wind in the data set on the previous 2 slides ago, you see that you can have a strong wind or you can have a weak wind. So you then work out the PD of A would be the PD of wind equal to strong and the PD of wind equal to weak. And you'll work out the number of instances that occur in the data set that have a value of strong and have a value of weak, and divide each of those by the total number of instances to give you the probability. Similarly, to work out the entropy now, the entropy is going to actually be based on the probabilities for that attribute having a specific value. We'll look at an example just now, it'll be a lot clearer. So if you look at the probability itself, how do you calculate that? Sorry, excuse me. And the probability is basically the number of instances containing that particular value for the attribute divided by the total number of instances. So if we look at an example, if you look at the case again where you've got the attribute wind and you're looking at a value of strong, the way you work out the probability is you count the number of instances in the data set that have a value of strong for wind. And in this case, we've got 6 out of 14, which gives us a value or probability of 0.43. Now to work out the entropy, we also work out probability values. And here the probability values are a little bit different. So we're looking at everything in the context of the attribute wind having a value of strong. So we know that there's 6 instances that have that value in our data set. But to work out the probabilities for the entropy, we're actually looking at those classes that will actually have how many of those 6 have the particular classes. So we have 2 classes in this case. We have no and we have yes, and we have 6 cases that have a wind value of strong. So of those 6 cases, how many have a label of no and how many have a label or target value of yes? And in this case, it's an equal number. So 3 of those 6 cases have a class of no, and 3 of the 6 cases have a class of yes. Okay, so just a reminder again as to why we're calculating this value. The reason for calculating this value is to use it in the algorithm that induces a decision tree. Now there are a number of different algorithms. We've just looked at 2 measures. Depending on the algorithm, other measures could be used. So the 2 measures we've looked at specifically are measures that are used by the ID3 algorithm, and that's what we're going to look at next. So if you look at the ID3 algorithm, it basically starts off checking the data set and checking if all the labels are of a particular class. So if all your labels, so if you don't have balanced data at all and all the labels of a particular class, then the decision tree is just a node representing that class. So 1 here represents one of the binary classes. So if it's all 1, then it outputs a value of 1. And similarly, if it's all 0, it will output a value of 0. The next check it does is to check that if there are attributes. So if there are no attributes, then it goes through and it actually will be a decision tree of just one node again. And that node will be the most frequently occurring label in S. If that's not the case, and usually it's very rare that you're going to have the first two, those are in case of errors, so those are just error checks. If that's not the case, then we need to determine which attribute has dominance. And gain is used to actually calculate which attribute has dominance, and we call that max att. So max att is we've calculated the dominance using the gain formula, that's equation 4 on your notes, for all the attributes, and the one with the highest gain is the one that will form the root of the decision tree. The algorithm does another check just to check whether all the instances in S if they have the same label, then it's just going to return a leaf node with that label. But again, that's just an error check. So once you've decided now that there aren't any errors in your data, you've got a data set that you can actually create a decision tree for, the first thing you do is you make the root of that decision tree max att. Now, after we've created the root, we don't want to consider that attribute anymore because we've already found a place in the tree. So we then look at A dashed, which is the original set of attributes, excluding that attribute max att. We then go through and for each value of that attribute. So, for example, if you took Outlook and Outlook was the node at the root of the tree, Outlook has a value of sunny, overcast, and rain. So the next layer in the tree will actually be the values of that. We'll go down, leading out from the values of those attributes to create the new child node at the lower end of the tree. So you'll have one arc coming out for a sunny, one arc coming out for overcast, one arc coming out for rain. And then the nodes at the end are the next thing that need to be now created. So if you find that there's no instances of that value in your, or no instance including that value in your set of S containing your data instances, then the leaf node just becomes the most frequently occurring label again in S. If that's not the case, the node that's being extended is not a leaf node. So just imagine now you've got your root node and you're now linking via the attribute values, namely sunny, overcast, and rainy, for example, if you'll have Outlook as the root, to the next node. If that node doesn't have that value, doesn't occur, so for example, if overcast doesn't occur in the set of training instances, then you take the most frequently occurring label, and that's the output for that node. However, if it does occur, then you've got to create a new subtree, and the subtree is created by calling up ID3 again, but this time ID3 is called up with the instances that specifically have that value in it. So that's the S dashed. So you can see S dash is instances in S containing the value of CV of A, and the now updated attribute set, which is the attribute set without the attribute that you've now just rooted. So just to quickly summarize again, we calculate the attribute set without the attribute that's just been added as the root. We then go through and check and see how we can create the leaf node. And the way we're creating the leaf node is we're now going to look at the set of S dashed, which is the instances that have this value in the data set. If that's empty, then we just add the most frequently occurring leaf to the parent by the attribute arc. If that's not the case, then we're going to call up ID3 to create a new subtree. Okay, so that's basically one way in which decision trees are created. This is one induction algorithm. There are other induction algorithms that can be used. In next week's touch, we'll look at completing the decision tree that we spoke about just now, and we're going to look at, in the next slide, we'll look at what it will produce if you apply ID3 to the data set that we had in the example slide, the one with the 14 instances, what decision tree it will produce. In the TAT next week, you're going to work through creating that decision tree using the gain formula that we looked at and using the algorithm that we've just presented. This is the example that we've looked at, the 14 data instances. So ID3 was applied to those 14 data instances, and this is the decision tree that it's produced. So what's very interesting, you can see that it didn't need to use the attribute temperature. That did contribute to the decision made as to whether netball should be played or not be played. So the root node is the attribute representing outlook, and the reason that would have been placed there is it would have had the highest gain value. And then the ID3 algorithm would have been applied moving from the values sunny, rainy, and outcast, moving down from those values. And as you can see, humidity was included and wind was included, but temperature was not included. So for next week's TAT, you will work through applying ID3 to those 14 instances to produce the decision tree. So you should come up with more or less the same decision tree. So decision trees are sometimes used alone to do classification, but they can be combined, and when they're combined, we say these are random forests. The whole idea of an ensemble is used to combine these trees. So if you remember from the first lecture on machine learning, we spoke about AdaBoost and XBoost, which are ensembles. So a random forest is also an ensemble. So essentially, your random forest is made up of a number of classifiers, and each classifier is a decision tree. The overall aim, like with each decision tree, is to perform classification. But what's interesting is that each decision tree doesn't have to be trained on all the training instances. And in addition to that, different techniques, different induction algorithms can be used to create the different decision trees. So the overall process in creating a random forest from decision, when you incorporate in decision trees, so you choose a subset, and that subset is then used to create your decision tree using a particular induction algorithm. So some of the decision trees could be created using ID3, some of the decision trees could be created using something else. Now, the interesting thing is you don't have one classifier now. Each classifier will produce a different class. So how do you decide what decision your random forest is going to come up with? Which class is it going to classify that instance as belonging to? So the technique that's used with that is majority voting, where majority of the classes, whatever their output, that's actually the output for that particular problem instance. So also remember, all the decision trees aren't trained on necessarily the same set of training instances. So you have your data set, and again it's divided into training and testing. And then that training set is further divided. A subset of that training set is randomly selected each time when you want to actually create a classifier using one of the induction algorithms to produce your decision tree. One of the advantages of random forests is it works very well when it comes to looking at the problem of overfitting and overcoming overfitting. So just a quick reminder as to what overfitting is. Overfitting is the case where you get very good accuracies when you apply your classifier to your training set, but in producing or applying your classifier to your test set, the accuracies are not as good. So you can see from the way the training set is divided into subsets, and each classifier is created using a different subset that actually contributes to preventing overfitting. So this is basically the only lecture that we'll have on decision trees. Next week you will complete part of your TAT will be on decision trees. And then the next lecture we're going to look at, so far we've looked a lot at supervised learning. When we looked at autoencoders, that was an example of unsupervised learning. So next week we're going to look at unsupervised learning, general machine learning techniques for that, and the first technique we're going to look at is k-means. So I'll stop there for today's lecture.